there is a special element. Oh, the recording is
I
now
hope
in
you don't
progress.
mind.
So again, thanks for giving me the opportunity to give a talk, and happy Halloween to everyone. In this talk, I will talk about the generalized 2-bit spaces, and in order to describe them, I will start from construction in pure algebra, and I will introduce partially multiplicative quandles. Partially multiplicative quandle, which I will abbreviate by PMQ, is a set with some structure. I will denote it by Q. So first of all, there is a special element, which I will call the unit. And then there are two operations. Both are binary operations. The first is called conjugation, and it's defined for all pairs of elements of Q. So it's a map from Q times Q to Q. And I usually write the pair of elements A, comma B is sent to A to the B. And the second operation is called partial product. This time is defined only on a subset. The domain of definition is some subset of Q times Q. And again, it's a binary operation with values in Q. And sometimes, so let me write this. Sometimes AB maps to the product A times B. Now, there are some axioms that these two operations must satisfy. In particular, there are some axioms only involving the first operations, giving rise to what is called quandle in the literature. And there are some other axioms involving only the partial product, giving rise to what is called a partial monoid. And then there are some axioms putting these two things together and giving rise to a partially multiplicative quandle. And these operations are called in this way because they want to mimic conjugation and product as in a group. So there are some axioms. Let me go over them. First, there are the axioms about quandle. The most important one is that A to the B to the C is equal to A to the C to the B to the C. This is for every A, B, and C in a group, you know that such an equality actually holds. And then there is the axiom that conjugating by A is a map from Q to Q, and it's assumed to be a bijective map for every A. And then there are some involving the units. So 1 to the A is always equal to 1, and A to the A is equal to A, and it's equal to A to the 1. This is the first part of the axiom. Now let's see those involving the partial product. Well, first of all, every element can be multiplied by the unit, and the unit is a neutral element for the. Second, the product is associative, and I will write this axiom in the following way, and I will put some quotation marks around this equal sign. So the axiom says that for A, B, and C in the set Q, either side is defined if and only if the other side is defined, first of all. And second, if both sides are defined, then they give equal elements in Q. And then there are some axioms that involve both structures together. There is this one, AB is equal to B times A to the B. And if you conjugate A by product BC, if this is defined, then it's also equal to first conjugating A by B and then by C. And the last axiom is that if you manage to take a product and then conjugate by C, then you can equivalently first conjugate and then try to compute the product. So these are, this is, yeah, as I said, an abstraction of what happens with conjugation and multiplications in a group. And I will comment later on why I am interested in the case where the product is only partially defined. But first, let me go to some examples. Well, the first, as I said, if G is a group, you can consider as a PMQ with usual multiplication and usual product, so full product. We will say that such a PMQ is complete. So the product is defined for all couples. Other example, if M is a partial abelian monoid, we can define A to the B equal to A always. And this is compatible with this axiom here in particular because abelianity. And we get PMQ. I will call it an abelian PMQ. Examples of this, of course, are in natural numbers, starting from 0. And here 0 is going to be the unit. My additive notation when the partial product is a product and is denoted with the plus. But another example to keep in mind is this monoid here. There are two elements, 0 and 1, as the multiplicative monoid on the set 0 and 1. Maybe I could write 1 here and say that this is the unit. And yeah, this is the unit, and this is an absorbing element for the product. And a third example I want to give, and this is related to the work of Ellenberg, Venkatesh, and Westerland, is the following. Let G be a group, and let C be a conjugation invariant subset of G. Then we can define Q to be the disjoint union of C and the unit. And we can declare the conjugation to be essentially the conjugation that we had in C, extended with the unit in the only possible way that respects the axioms. And with trivial product. Trivial product means basically no pair of elements can be multiplied except those required by this axiom. So whenever you can multiply two elements is because one of the elements is the neutral element. This gives a PMQ. So there are some properties that a PMQ can satisfy or not satisfy, and I want to point out one. So Q is augmented if an equality of the form AB equal 1 holds if and only if A and B are already equal to 1. And for such, so basically the only way to factor the neutral element as a product is using again twice the identity, the neutral element. And in this case, set notation Q plus will denote the set Q minus the identity. Another characterization of Q is the following. For every PMQ, you can define a map of sets from Q to this PMQ here by sending 1 to 1 and Q plus to 0. This is a well-defined map of sets, and Q is augmented if and only if this is a map of PMQs. By the way, I noticed that I should tell you what a map of PMQs is, and it's a map of sets that sends the unit to the unit, respects conjugation, and respects the partial product. And in particular for the partial product, I mean that if two elements A and B in the source are multiplicable, then f of A and f of B must be multiplicable, and the product fa times fb must be equal to f of AB. Let me mention another example which for me was motivating. So there are this for every D, there is the symmetric group SD on D letters, and out of this you can define a certain PMQ as the geo stands for geodesic. So as I said, this is just SD, the conjugation same as in SD. The product, whenever defined, so the product is contained in the product of the group, but only defined sometimes. Some pairs, sigma tau of permutations. And here the word geodesic comes into play. We say that if we consider the word length norm with respect to all transpositions, this is a norm on the symmetric group. And if you take two permutations sigma and tau, you can compare the norm of the product with the sum of the norms. And norm of sigma plus norm of tau is always greater or equal than norm of sigma tau. And we declare a pair to be multiplicable if equality holds. Anyway, I don't want to go into the details of this. I want to mention this as a motivating examples, and we will see later why, but I would like to focus in this talk on the general theory. And I would like to, yes, to give another piece of terminology. So Q is complete. I think I already said if it's the product is always defined. So we can call such a PMQ a multiplicative quandle without the word partially, and we can consider a category of multiplicative quandle as it's the full subcategory of the category of PMQs whose objects are complete PMQs. There is so an inclusion factor, and this inclusion emits a left adjoint, which I call the completion factor. How is this described? So given Q, we send it along the completion to Q hat, and this is obtained by completing Q as a monoid, and then you extend conjugation. You write down essentially the first formula that you can think of, and it works. There is a little, I mean, this axiom here will force you to, after you complete the monoid, you must take a little quotient to enforce that axiom, but otherwise, the construction is not complicated, and there is this little proposition, namely that you have a unit of the adjunction, which is a map of PMQs, and it goes from PMQ to its completion, and this map is always injective. Okay, so we can always consider Q as a subset of Q hat. This is similar to what happens for completion of partial monoids to monoids. Okay, so I want to mention one thing. I said what is a complete PMQ. but I didn't say about these examples which ones are complete. Of course, the first one is not going to be complete unless G is a trivial group, and the other ones actually are all. Sorry, one is not augmented, but the other ones are augmented. And in fact, yes, which are the complete ones? These are complete. One is complete. 3 is not, because the product is trivial, so there are pairs that cannot be multiplied unless C is empty, and also 4 is not going to be complete. But which ones are augmented? Basically all of them but one. And today I want to focus on augmented PMQ. So today only augmented PMQs. Okay, now I can pass to the topology part of the talk. So how do I relate this construction to Hurwitz spaces? Well, first of all, Hurwitz spaces are usually about the following. You have the complex plane. For simplicity, let me draw the standard unit square and do the following construction inside there. So in Hurwitz spaces are usually about configurations of points in inside the unit square. For example, this is a configuration, and it's a finite configuration of some k points as contain the unit square. And usually what one does is, I mean, one considers an additional datum attached to this configuration, which is a monodromy. And a monodromy is usually defined as a group homomorphism out of the fundamental group of the Bianchi plane. So what one does is one consider y1 of C minus P. And I mean, if we want to consider the fundamental group, I have to be careful that I need a base point. So here's my choice of base point below the square, so it doesn't interact with the points that I remove. And yeah, I mean, usually one consider this group, and you know, this group is going to be isomorphic to a free group on k elements. Abstractly, it's a free group, and more concretely, you can exhibit it as a free group by considering, for example, this system of loops. You draw some embedded loops that only touch at the base point, and for each point in the configuration, you have a loop spinning around it clockwise. And such system of loops exhibits this fundamental group as a free group. And yeah, as I told you, you now you fix your favorite group G, and the point in the Hurwitz set is classically the datum of a configuration P and a monodromy in the form of a group homomorphism from this group to G. And now I want to do the same thing, but with PMQs. So first of all, I have to introduce a fundamental PMQ. So I will let Q of P be a certain subset of the fundamental group. And this is the union of the identity and the conjugacy classes of the drawn loops. So I will put not only these loops that I've drawn, but also all of their conjugates inside the fundamental group. Now, a fundamental group of a space has the following property: a conjugacy class in it corresponds to a free homotopy class maps from S1 to your space. And the free homotopy classes I'm considering are those of these red curves that I'm drawing now. There is one small loop spinning around each of the points of the configuration point clockwise. So what is the PMQ structure here? Where conjugation comes from the group, and the product is declared to be the trivial product. Q P is PMQ with trivial product. And you can appreciate that you can also think to declare the product to two elements here are multiplicable if their product in here is actually contained here. But then you realize quickly using the Abelianization of the fundamental group that this only happens if one of the two factors, at least one of the two factors is the neutral element. Yeah, and then I would like to define the Hurwitz set for Q is a set of pairs P comma psi, where P is a finite subset, possibly empty, and psi is a map of PMQs. From fundamental PMQ to Q. And I want to think of this as the monodromy. And I will call the values attained by psi on these small loops spinning around the points, we call them local monodromies. They are elements of Q. Now, according to this definition, this could be empty because it's not clear at all that there exists PMQ morphisms like this, but actually this is the case. So psi, such a map psi is uniquely determined by values on the drawn loops. So in other words, this was a free group on K generators. This would be a free PMQ on K generators. So it's a proposition 1 2. And then since Q is augmented, let me also say what subset I'm going to be interested in. This is the subset of pairs P psi, where psi is an augmented map. And by this, I mean that psi inverse of the identity is just the identity. So what I want is that the neutral element, which is represented by this loop, is sent, of course, to 1 because it's a map of PMQs. But every other non-trivial loop in this fundamental PMQ must be sent to one non-trivial element in Q, so an element of Q plus. The rationale for this is that you should be able to forget if a point has a local monodromy, which is neutral element, in some sense the point doesn't exist. You want to think as point to be vanishing or transparent. What is the topology on this set I want to consider? Well, here I would like to appeal to your physical intuition. So, I mean, to declare a topology on a set, I have basically to tell you for every configuration what is a system of neighborhoods of this. So let's consider the following configuration. There are 2 points. And what about the monodromy? I will just tell you, as I told you, I just have to tell you where these 2 loops are sent to. And let's say that they are sent to 2 elements A and B in Q. And then I ask, if I perturb this configuration, what do I expect to see? So if you think of this as particles moving in the unit square, if I perturb this configuration, I will get a new configuration where the new particles are close to where the particles are. Like that, there is no reason why in a small perturbation suddenly a new particle should appear here. More precisely, let us fix small disks around the particles. I mean, this disk goes out of the square. This is not a big problem. In a small perturbation, we expect the following. Each of the original points splits as one or more points. For example, like this. No points appears outside the red disk, so all points stays close to where points originally were. And then there should be a conservation of energy or mass principle, which in our case would be a conservation of monodromy principle. So the loop, this loop here that I've drawn here and it spins around this red disk, I can draw it also here. Well, I can draw it, but it's no longer a loop in the fundamental PMQ. It's only a loop in the fundamental group. Right. However, I can factor such a loop as a product of inside the fundamental group. I can factor it as a product of smaller loops that are in the fundamental PMQ of this configuration. For example, like this, and similarly, I can do like this. Now, in a nearby configuration, these 5 points and these 5 small loops I've drawn will have local monodromies A1, A2, A3, and B1 and B2, given by the new amount of PMQs. And the requirement is that that the product of A1, A2, and A3 should be equal to A, because this is what happens in the fundamental group. And similarly for B. So for every configuration and for every choice of disks, you get a neighborhood consisting of all other configurations that satisfy all of these properties, and this defines the topology on the Hurwitz set. And as a first proposition, let me say that if C in G is a conjugate invariant subset, then you can consider this disjoint union of C and a disjoint neutral element. This is going to be an augmented PMQ. You can take its positive part, and no surprise, this is just C. So this is just to motivate what this expression means. This is an instance of for Q plus, for a particular choice of Q plus. And this is homotopy equivalent to the disjoint union of the spaces for n CG, and these are the spaces appearing in the work of Ellenberg, Venkatesh, and Westerland. And the proof of this theorem is that when C, well, if you consider a PMQ with trivial product and it's augmented, then basically there is no way to factor a non-trivial element as a product of two non-trivial elements. Correspondingly, the only thing you can do to perturb such a configuration is to move a little this point inside this disk and this point inside this disk. Yeah, another proposition which motivated me to define this generalized Hurwitz space is the following. If you consider this geodesic PMQs and consider the corresponding Hurwitz space, at least the part where local monodromies are non-trivial, this contains a component which is homotopy equivalent to the moduli space MGN, at least whenever G is greater or equal than 0, N is greater or equal than 1. D has to be greater or equal than 2, and most importantly, D has to be greater or equal than 2G plus N minus 1. So this is the moduli space of Riemann surfaces of genus G with N ordered and parameterized boundary components. For example, is the moduli space occurring in the Harrer stability theorem or in the work of Madsen and Weiss, the stable homology of moduli spaces. Unfortunately, N must be greater or equal than 1. So MG is not achieved by this construction. This is another motivation for the construction. Let me now consider the following case. Suppose the Q is equal to Q hat, so it's complete. Then what can we say about pure Q? Well, what happens is that pure Q is homotopy discrete and it's equivalent to the set Q union another singleton, which I called empty. And the reason is that if you have a configuration, either is the empty configuration, so no point, and trivial map from the trivial PMQ to Q as monodromy, or you have some points, you have some local monodromies, but since everything can multiply to everything, you can let this configuration implode and homotop it to a configuration where there is a single point in the middle, and its local monodromy, let me call it omega, is what the product in Q was of all of these small local monodromies. And this is well defined because Q is supposed to be complete. Okay, write omega in quotation marks. So this is a motivation for why I'm interested in partially multiplicative quandles and not just in multiplicative quandles, because with multiplicative quandles, the spaces that you get are rather uninteresting from the point of view of their topology. But this can be also seen as a, there is a counterpart to this example, which is the following proposition. So if you have a Q is augmented, then there is a natural map from pi naught, the set of components of Ur Q plus. And this natural map, I want to call it the total monodromy, and it has values in Q hat. It's defined as you expect. You take any configuration and you multiply the local monodromies. The multiplication is not allowed in Q, but it's always allowed at least in Q hat. So you do this multiplication here, and this is actually a bijection of sets. Now this proposition doesn't tell you much about how to enumerate kinetic components of these spaces, but at least it tells you how to think of this set. This set has some additional structure, and in particular it has a universal property. This is for, this makes sense for Q augmented. But I want to consider Q augmented. Okay, now I want to pass to, well, what about Q, generic Hurwitz space? What can we say about the topology of this Hurwitz spaces in the case in which Q is not complete? For example, can we compute homology groups? So in order to compute homology groups of spaces, it's a good start to have a cell decomposition of such spaces, or and so the next part of my talk is about cell complexes. So let me start with a small observation, namely that if Q is augmented, then also Q hat is augmented. This is just little observation. So if the only way to factor 1 inside Q is as 1 times 1, then the same holds in Q hat. So given an augmented Q, now let Q be augmented. I want to introduce a certain bisimplicial set. Define a bisimplicial set, which I call RQ, and R stands for array, because the elements of, if you go in by degree P comma Q, then an element in this set is going to look like an array as follows. You have a grid, an array, so a grid, and there are there is a total of Q plus 2 columns, where a column is, one of the drawn vertical segments. So don't think of the cells, think of the vertical segment. There are Q plus 2 many, and there are P plus 2 many rows. And how do I want to decorate this grid? This can be arbitrarily large. I want to put on each node of the grid an element of Q hat. So here I will have an element A00, here I will have an element A01, A10, and so on. Here I will have A P plus 1, Q plus 1. Here, for example, I have A0, Q plus 1. And Aij is in Q hat. Okay, this is a big table of elements of Q hat. What are now the degeneracy and phase maps? So degeneracy map, there are vertical and horizontal degeneracy maps, of course, and they are given by adding a row or columns, or a column of ones. For example, you could add here a new column, and on each node you put the neutral element. For phase maps, the thing is a bit more tricky. So the basic idea is that you want to collapse 2 consecutive rows or 2 consecutive columns. So for example, you might want to collapse these 2, or you might want to collapse, well, let me add, because I don't want to use the degenerate one. You might want to collapse these 2 consecutive columns. When I say collapse, the idea is that you multiply consecutive 2 consecutive columns or consecutive rows. And now there is a little caveat, namely, okay, if Q and Q hat are abelian, that's the end of the description. But if they are not abelian, so if conjugation is a non-trivial operation, Then here, when we multiply columns, we have so here some conjugations are involved. For example, if you multiply this column with this column, so this one, at some point you will multiply this element by this element in Q hat fair. But when you multiply this entry with this entry, you should really first conjugate this entry by this entry here. Okay, this is just to ensure that what you get at the end is a bisequential set. And let me skip on the details that you can write a little complicated but formula, but you can write a formula for this. What's the idea between this bisequential set? When you geometrically realize it, for every array p comma q, you will get you can get a configuration of points in the square by putting, I mean, the simplicial coordinates will tell you horizontal and vertical positions for these inner lines. The outer the outer sides of the square, of course, account for the outer side of the unit square. And you will put, whenever there is a node whose label in Q hat is not identity, you will put there you're going to put there, this is for example Aij. If Aij is non-trivial, you will put here a point in your configuration, and you will require that the monodromy around this loop is equal to Aij. This is how you get from the geometric realization of points in the geometric realization of this bisequential set. You give rise to points in the orbit space. However, there are two problems. Namely, we don't want points on the boundary of the square, and we don't want local monodromies in Q hat. We only want them in Q. So that's why we have to introduce this. There is a sub bisimplicial set, so of non-admissible. This is a sub bisimplicial set of those arrays having either of both of the following bad features. The first is that there is a boundary entry which is not one. So boundary entry means one entry on the boundary of this grid. And the second is that some entry is in Q hat minus Q. So it's not in Q, it's only in Q hat, but not in Q. This is a difference. Sorry, this is a sub bisimplicial set. And yeah, I mean, the discussion of before tells you that when Q is augmented, then there exists a continuous bijection from the difference of the two geometric realizations to this Hurwitz space or Q plus. This is only a continuous bijection in general. Now, to make it into a homeomorphism, we have to assume something about Q. So if Q is locally finite, and I will tell you in a moment what this means, then it's a homeomorphism of locally compact Hausdorff spaces. I mean, these are anyway Hausdorff spaces. So yeah, so I have to tell you what it means to be locally finite. So definition: Q is locally finite if for every A in Q, there exists only finitely many factorization of A as a product A1 up to AR with AI different from 1. So every element might be factorable as a product of non-trivial elements, but we require that every element admits only finitely many factorizations of arbitrarily length. Okay, so R can vary, and yet for every A there are finitely many factorizations. If this is the case, then we say the Q is locally finite, and this basically is hypothesis to ensure that, yeah, that this difference is a locally compact space.
Can I just ask about the order of the quantifiers here? Are you assuming there are finitely many of these for any given R, there are only finitely many, or?
No, that's exactly a stronger condition what I assume. So if you fix A and you let R vary and you consider all possible factorizations of A as arbitrarily many, finite number of course, arbitrarily many elements, and you require all of them to be different from 1, because it's easy to plug as many ones as you want, of course, then there are only finitely many possibilities.
Okay.
Example, if you take Q to be a trivial PMQ, so basically no product, but only the products with a neutral element are allowed, then this is going to be a finitely locally finite PMQ for simple reasons. Also, the geodesic PMQs arising from symmetric groups have this property. In general, if your PMQ is graded by natural numbers, in the sense that there is an additive grading which is conjugation invariant and additive when you manage to multiply two things, and only the identity has degree 0, then you are in a good shape, at least if Q is has finitely many elements in each grading. I mean, this I just want to say that being locally finite is a condition that in many concrete situations holds. And yeah, I would like to in particular if Q hat is also locally finite. So suppose that Q is any PMQ, and not only Q but also Q hat is locally finite. Then there is an isomorphism between the compactly supported cohomology of Q plus and the relative cohomology of the realization of RQ and the realization of non-admissible Q. And if I write this isomorphism as this is hardly ever going to be true, for example, because in both cases there are probably infinitely many connected components, and you know, cohomology of an disjunctive of many spaces is the product of the cohomologies, but here I would have the direct sum. So however, if you fix a total monodromy in Q hat, and you just consider this statement as comparing the part of this space and the part of this relative space with total monodromy, that fixed element of Q hat, then this becomes a precise statement. And the good thing is that, yes, that this guy is a relative CW complex. Like here you have a cellular cochain complex. So this could be fed into computations. I mean, one can try to make a concrete computations. And in this spirit, let me now present a result that I hope the audience will enjoy. Way to rephrase all of this. So let me define for a PMQ, augmented PMQ, let me define the PMQ ring. Okay, this is something like the group ring of a group, of the monoid ring of a monoid. And as it's first of all an abelian group, and it's a direct sum of copies of Z. One, so there is a generator bracket A for every A in Q. And then I declare the product to be the following. Bracket A times bracket B is equal to bracket AB if AB is defined and it's 0 otherwise. Okay, so this is a ring, and it's if Q is augmented, this is an augmented ring. That is, there is a map from ZQ to Z that basically sends bracket 1 to 1, and it sends bracket A to 0 for every other A. Yeah, you can now consider the bar complex. B dot of Z, comma ZQ, comma Z. This is, for example, this is a chain complex of billion groups. It is the one that, for example, you can use to compute Tor of Z, comma Z over this ring. So, but recall that the bar complex is first of all a simplicial abelian groups. I mean, before being a chain complex, it's a simplicial abelian group that you then totalize to a chain complex, and the nth level is the abelian group. I mean, just to write down what it is, you take this long tensor product of twice the module and then the nth power of your ring. All tensor products are over Z. And now the fact is that this can enhance this to a simplicial augmented ring. So yeah, an augmented ring is in particular an abelian group, and a simplicial abelian group can sometimes be enhanced to a simplicial augmented ring, which denoted, let me denote this by this curly B of Q, just to say that this is a simplicial object in augmented rings. How do you do? Well, first of all, you have to give this guy a ring structure, and there is an obvious one, namely tensor product of rings, and this is the wrong one, because if you give this ring structure, then the phase maps of this simplicial abelian group are not going to be ring homomorphisms. So you have to twist, and twisting. So there is a twisted tensor product structure on this tensor product of rings, which gives a ring structure on Bien, and with this ring structures, this becomes a simplicial augmented ring. Another theorem that it's more or less a rephrasing of consequence of what I've said before. So let Q be such that Q hat is locally finite. Technical condition, but then the compactly supported homology of for Q plus is isomorphic to the next algebra over this simplicial ring of Z comma Z. Here Z is considered as the constant simplicial ring with a value Z, which if you want is a simplicial module over this simplicial ring. I mean, this result can be well compared with work of Ellenberg, Tran, and Westerland on comparing twisted homology of braid groups with Ext over shuffle algebras, or more recent work of Huang on comparing twisted homology groups of Artin groups of type B with again some S groups over where some bimodules over some shuffle algebra is involved. I mean that this is another kind of result in the same similar spirit. And how much time do I have left? I forgot what time I started.
You started a couple of minutes after.
Yeah,
Thursday,
let me then just make two observations on this. The first, this is an isomorphism of rings. There is a ring structure here coming from the fact that, yeah, I mean, there is a map from Q plus times your Q plus. I want to call the multiplication with values in Q plus. And this map basically takes two configurations and juxtaposes them. And I mean, you have to take care of the monodromies. You take care of the monodromies this way. So if you think this construction, of course, you have to squeeze the widths of these two squares to make this work. This is an open embedding of this space into this space, and this corresponds to, I mean, this gives rise to a product structure here. And this is the Yoneda product, and I claim that these two are isomorphic as rings. Of course, you could say, why don't you consider homology? Like this for Q plus is also a by this operation becomes an E1 algebra essentially. So the homology of Q plus is a Pontryagin ring. And here I have compactly supported homology, which really screams Poincare duality, right? If we were able to replace this compactly supported homology by homology, we would be by Poincare duality, then we would understand the Pontryagin ring. And well, this is not always possible. One can give the definition, which, and I will conclude with a question about this definition. So PMQ, which is augmented and locally finite Q. So take Q, make it augmented and locally finite. We said that this is Poincare if each component of Q plus is a manifold. Or at the very, very least, a homology manifold, or you can fix your favorite ring, R, and I said this is a R homology manifold, and you say this is R Poincare. And the question is, I mean, characterize, classify Poincare PMQs. This is a question I would like to see progress on. Okay, thank you for your attention.
Just thinking that questions? Any questions or comments?
I have one. Is there any like arithmetic, like an application you have in mind for this, like more general setup?
Maybe. I would like, yeah, I mean, for arithmetic applications, you need to have a algebraic geometric counterpart of this spaces, right? I mean, if you think of the work of Ellenberg, Venkatesh, and Westerland, the way it works is there is a scheme or a stack, I mean, something algebraic, and if you take its complex points, its associated analytic space, you get such a space. Then you understand rational homology of the space. You do something about étale cohomology of the algebraic counterpart, and then you use that one to get some arithmetic statements, arithmetic statistics, right? So in order to start mimicking this this strategy, one would need an algebraic counterpart of this thing. So another question. Now, if you prompt me, so given a Q, let's say, that is also augmented and locally finite, find a scheme, and given, let's say, also given an element omega in Q hat, total monodromy. So we are going to select one component of the Hurwitz space. So find a scheme whose complex analytic space is basically where Q, the component of total monodromy omega. This is a question I would also like to see answered. For in the case of trivial product, this question is, I mean, this question has been settled, and I guess by Fulton firstly, and then this allows this comparison. In this generality, I have some idea of how to get such a scheme, but I'm not good enough in algebraic geometry to check that this actually works.
Yes. Craig, you have been holding your hand. Go ahead.
It's very easy to hold my hand when I just have to press a button. I was curious in this theorem that you're presenting, that the compactly supported cohomology is the cohomology of this simplicial ring. If one takes Q to be the completion of a conjugacy class or a conjugacy closed subset of G, what sort of, if does it I assume it does not apply. It's not locally finite. Is that correct?
So if G is a finite group, and then conjugacy class C is also finite, then the completion of this PMQ is going to be locally finite.
Oh, okay. You got the grading.
Yeah, exactly. You have a grading, and you know there are finitely many components in each grading for spaces.
Then do you have an idea?
Yes.
Do you have an idea of what the cohomology computation looks like for those?
Oh, it just looks like yeah.
Oh, sorry, this is the disjoint union of the Hurwitz spaces then. Is that
yes,
right?
in that case, yes, that example of PMQ is Poincaré for a very simple reason. If you take Hurwitz space where there are no collisions, there is no place for singularities of any kind.
Yeah.
After all, configuration space of points in the plane are manifolds, and
Yeah.
covering spaces thereof are also manifolds. So this is the Poincare case, and yes, you will get the homology of Hurwitz spaces, or if you want the compactly supported homology, which is the same by Poincare duality. Here there are some degree shifts. I mean, passing from here to homology, of course, involves some mild degree shifts
Sure.
that one has to be careful about, but apart from that, yes. So you get you get the same kind of statement. And I mean, also this this thing here, if you think this, it's this ring Z of Q is going to be a rather trivial ring. Basically, the product of every, apart from the identity, the product of any two disguise is 0. So this bar complex kind of coincides with its homology.
Yeah.
And it turns out that yes, that this P, that this X can be computed over the ring. You can apply homology to be.
Yeah, this is the
Yeah, I
shuffle.
mean, exactly. This exactly.
If
You
and
get-
then I assume that if you then allow multiplicate the quandle, if you allow the multiplication in the quandle inside of G, then it stops being locally finite, so one can't easily apply this theorem at that point.
So, can you be more precise?
Sorry, if you take the a conjugacy closed subset of G and regard it as a quandle in the same way, but make it partially multiplicative by saying allow multiplication to happen if it makes sense within that subset of G. This presumably stops being locally finite, so one can no longer apply this result.
Well, this depends on case by case. Sometimes, in general, yes. Okay, there are 3 levels of generality. In the most general case, what you suggest, so declaring a product to be there whenever it lands inside the subset and otherwise be undefined. Well, this doesn't give rise to a PMQ in the first place, not always. There are some conditions for this to be, first of all, a PMQ. It's a little technical condition. When it gives rise to a PMQ, also very often it will not be locally finite and not even augmented. Like being locally finite is a stronger condition than being augmented. Because if you can factor the identity as a product of elements, then you can write arbitrarily long products. And even if it is yes, if instead it is locally finite, then yeah, it can happen. It can happen that everything goes through. Think of your group is Z, your subset is a abelian group, so any subset is conjugate invariant. Take the set of elements, natural numbers between 0 and 10, and this is going to be Poincare abelian and Poincare PMQ.
Okay.
I think we are terribly over time, so let me not hold the whole room accountable here, and let's just thank Andrea for the very interesting talk, and continue the discussion afterwards informally. But now it's basically say that we are done. Thank you very much, Andrea.
Okay. Thank you again for your attention and possibility to speak.
Thank you, Andrea. That was very interesting.
Oh, that's great.
Yeah, nice talk. And I didn't say that because I heard my name.
Are you celebrating Halloween?
What's that?
Oh, the Halloween, yeah. Well, you're celebrating your name mentioned.
Lots of candy if you'd like.
Okay, great. I have a pumpkin.
Very nice.
With,
Wonderful.
I made it yesterday. It's a true pumpkin. Actually.
Oh, that's nice.
Yeah, I carved it. I with together with my girlfriend, we carved it yesterday.
It's a
And we are going
configuration of, it's a
we have to-
configuration of three
Sorry?
triangles. It's a configuration of three triangles on a sphere.
Yes, exactly. Yeah. You see, it also we also use some seeds to make the eyes. I don't know if
Oh,
it's
yeah.
visible.
That's really great. Yeah.
Wait, I saw someone who was with the mask. I saw someone with the mask.
That was Sasha.
It was me.
Ah,
That's-
okay,
That's not for Halloween. Sasha just does that
Yeah.
every week.
okay.
What?
I didn't know.
What did you say, Calista?
I said that's not for Halloween. You just wear that mask every week.
Yeah, to cover my face, basically. Yeah.
Every mask is a
Which is
Halloween
even
mask.
uglier. Yeah.
I've been telling people that I'm dressed as Charles Manson, but just because I kind of bear in.
Oh, yeah, we was apology beers at 4:45, as Calista announced in her announcement. Yeah, meeting in the courtyard as usual. I wish everybody who is connected by Zoom would be able to join us, but you know,
Alas.
next time, perhaps.
All right.
So Andrea, if in one of your theorems, if the quandle is not locally finite, and when you said that your what was it? Continuous bijection was a homeomorphism of locally compact spaces. So the finiteness of the local finiteness of the quandle, what did it guarantee?
Oh, it guarantees that the spaces are
all
locally
spaces
compact.
are locally compact, or only
Yes.
one? Or is it true that one of the spaces is always locally compact and it only extends to the other one?
It's true that at least one of the two is not, and I remember that one of the two, the source. I mean, you're basically comparing a space which is not. I mean, it's the difference between two CW complexes.
Yeah.
And if in a CW complex you have infinitely many cells touching on their boundary some point, some lower cell, and this is not not going to be locally compact.
Right.
And the issue now is that so the source is not going to be locally compact in general, and the target maybe. I forgot. I forgot if it is. Yeah, I don't remember if I ever checked, but anyway, I didn't focus too much on this question because in the cases that I needed, primarily this, well, besides, I mean, the trivial product case, let me say the more classical case, the case of geodesic symmetric groups, all of the finiteness properties that one needs are satisfied. So yeah, I didn't study this question.
Okay.
I mean, I didn't study it deeply.
Yeah, you obviously studied the most interesting case, of course. All right. Yeah, and also it's surprising that you got your main theorem for the indeed for the cohomology with complex force rather than for the homology to start with.
Yeah, but that's more or less related to the fact that this cellular structure is not really I mean, it's a difference of CW complexes is not a CW complex, or better, it's not the cells in the difference don't give a cell structure, and so the only
it means that because it means some zero cells, or what's going on?
I mean, just consider a sphere with circle with CW structure with one zero cell and one cell, and then remove this subcomplex, which is the zero cell. What's left is not is a segment, is an open segment, and it's not. I mean, it's a CW. It has a CW structure with infinitely many cells, but the single one cell is not a CW structure on that space. And so this
using this compact
compactly supported,
like compact, taking the 1 point compactification.
Yes, precisely, or taking. I mean, when the Q-hat is locally. When Q-hat is locally finite, what happens is that each component of the geometric realization of RQ is compact, and the compactification that you take is just RQ essentially. So yeah, maybe I mean, writing compactly supported cohomology is just because it's something that has a name in the literature, but the statement, yeah, the first statement I wrote is a bit of a tautological statement.
Okay. Thank you. Yeah, thank you. It's very interesting. Would you be I want to post, oh yeah, by the way, maybe I should stop recording, but can I